Why don't we go ahead and get started, and the others will join us. We were just getting to the point talking about contrast agents, and we said that we were talking about gadolinium and the fact that as a contrast agent, it works as being a paramagnetic substance, and we talked about what diamagnetic, what a paramagnetic substance is, and what a ferromagnetic substance is. Uh, so, uh, Michael, how does gadolinium, what does it do to the tissues which allows us to see it as a contrast agent?
Okay, so gadolinium, because it's a paramagnetic molecule we talked about later yesterday, has a bunch of unpaired electrons, and therefore it causes interactions with the adjacent water molecules or the adjacent hydrogen atoms, and it essentially causes shortening of the T1,
Right.
and that's
And,
the
and
thing that
if you remember back, what caused shortening of the T1 from a physics standpoint? What's happening? What occurs that shortens the T1?
it is. I think it's the So it's when they become dephased. It's as the protons are becoming out of phase, they're starting to dephase. So
No,
it's
the phase is T2.
oh, okay. I'm getting it
And if you
mixed up.
remember, T1 is the time it takes for one standard deviation for the nuclei for the bulk magnetization vector to go to from 0 after the 90-degree pulse in the z direction up to one standard deviation of about 62% of the maximum value in the z direction. So what governs now, and if you remember, the bulk magnetization vector in the z direction is determined by the number of protons pointed up versus the number that are pointed down, the number that are in the high versus the low energy state. After the 90-degree pulse, we equalize those two populations, so they average to 0, so you have no component in the z direction. But over time, you'll drop more nuclei into the low energy state, which means that you'll have a surplus of the low energy state protons, and therefore you'll get a non-zero bulk magnetization vector in the z direction, which will eventually go up to the maximum value. And if you remember, the maximum value is really kind of determined by the tissues and how hot the tissues are. If we put everything down to absolute zero, then you'd have a very big bulk magnetization vector. But it's several million, it's a million times stronger than it could, smaller than it could be, because the thermal vibrations in the tissue keep knocking the nuclei out of alignment. If you remember when we talked about that. So the bottom line then is if you shorten the T1 time, then you're doing something to make it much more efficient for the nuclei to drop back down into the low energy state after you've equalized the population of up versus low down spins, right?
Okay.
And we said that was actually another word for that is the spin lattice relaxation time, and therefore the energy, most of the energy that comes in uh, to allow the nuclei to absorb or emit energy of exactly the right packet by quantum mechanics to allow it to transition from one level to another level uh, is basically the equivalent of a photon that has a frequency of the Lamar frequency. And most of those come from the vibration of the large molecules. So, and that's called the lattice.
Right.
Now, what a paramagnetic substance does is it's a big molecule like gadolinium on top of DTPA. So that's really part of the lattice. That's part of the big macromolecules of the structure, not the protons, not the other spins. So when you bring in a paramagnetic substance like gadolinium that has many unpaired electrons in the outer orbit, then you're basically adding a huge magnet with these unpaired electrons to the lattice itself, which when it vibrates then spews out many, many, many more times uh, 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 photons at the Lamar frequency. So because of that, it increases the efficiency of the nuclei dropping back down to the low energy state, and it shortens the T1 time. So it's basically because gadolinium is added to the lattice, but because it has all these electrons as magnets that aren't paired, it can much more efficiently stimulate the protons of the hydrogen to be able to release energy and fall back into the low energy state, which then makes the population of up versus down no longer equal, and that causes the Z component to rise in the from zero up to its baseline value.
Okay.
So that's basically how paramagnetic substances work. And it's because of those unpaired electrons in the outer orbits. And if you notice here, this is just a couple of graphs here showing that the
Second,
efficiency that
sorry, can you
this
hear me?
occurs, this is basically the signal intensity uh, versus concentration. Or I'm sorry, this is the T1 time versus concentration. And notice how it drops almost exponentially down here to near zero if you give enough gadolinium.
Can you hear me at all?
Yes.
I'm sorry.
Yep.
I'm not able to see your screen. I don't know if anybody else, if I'm the only one having trouble.
Can't
If I
see
am, I could
this.
relog in.
Okay, why don't you relog in? Because it
I could
should
see
be
it.
showing it.
You can see it? Okay.
Yeah.
Okay, so Michael will relog back in here. So as I was saying, this just shows how the T1 time drops with concentration of gadolinium. At both, and notice it happens about the same amount, independent of whether it's 3T or 1.5T, and only slightly the concentration of other macromolecules in the area only changes it slightly. Uh, Notice, however, that iodine actually has a pretty significant effect, and that's why some people think that you should not put an iodine uh, when you do arthrograms, you shouldn't put iodine in the agent. But it's what you actually see here is that iodine actually makes the T1 shortening more efficient at lower concentrations. So if you put iodine in it, you could actually use a lower concentration of gadolinium. And maybe one of the reasons why uh, some of the times you'll see that you'll have variations in the signal intensity of the fluid when you do an arthrogram. And if you put in a uh, iodine, it does change the characteristics a little bit, but other tissues don't. Yes.
So the iodine will act with iodine. You're going to get more signal on your T1 sequence. It's going to shorten, right? The T1 milliseconds has gone down.
Yes, that's correct. Now, on T1, it shouldn't if you're using a good T1 sequence. On T2, it will. Because what happens if the concentration is too high, what you'll get is also T2 shortening. And if you give the iodine, you'll have T2 shortening. So if you have a T2 weighted image, you'll see lower signal intensity. That's one of the reasons why we want to use very dilute gadolinium, is because I still like to have high signal intensity on the T2 weighted images.
If you, does the iodine have a T2 effect in and of itself, or it's just affecting?
No.
It's just the gadolinium it's affecting.
Yeah.
All right, and then when you do very concentrated gadolinium, though, when you mess up your mixture, doesn't the T1 get short eventually too, or long? And eventually it blackens your T1 sequence.
No, that's not. It does not. The T1 doesn't get long. What happens is you start shortening the T2, and if you shorten the T2 time below the TE time, then all the sequences will get darker. But it's not because of a change in T1; it's because of a change in T2. It means by the time you get your echo, all the signals died out, and that's a T2 effect, not a T1 effect.
Okay.
And that's the other thing you can have if your TE is too long on your T1 weighted sequence. When you add iodine, you can get loss of signal intensity, but that's a T2 effect. Okay. And then we can see if you just look concentration and signal intensity, which is normalized, you can see that there is a sweet spot here where you shorten the T1, but you haven't shortened the T2. And then you start dropping off if it gets too concentrated, because then you start having a T2 effect, which shortens the T2 time of the tissues. I also noticed that there's slightly different concentrations at 3T versus 1.5T. At 3T, you can use a little bit less concentration of your agent. Now, if you look at this, there's actually very little magnetic differences between at 3T and 1.5T, but you'll find on your images that at 3T, you often, it looks like you get much better enhancement than at 1.5T. So people tend to really like higher fields for contrast enhancement. And that's a large part probably because of the improvement of signal to noise. And then this just shows for heavily T1 weighted images. And this just shows, again, the importance, and we've talked about this before. Here's a case, this is someone who had a resection for a tumor. They were doing a scan for determine whether there's recurrent tumor. This is the T1 pre. It looks like the area is fairly low signal intensity, but no fat in it. T1 fat sat post contrast, it looks like it's very bright here. And one of the most common errors I see over and over again here in Southern California is that people will then call this enhancement, and therefore this would be recurrent tumor, and therefore they'd go in and start doing biopsies and resections. But you have to compare it to a T1 fat sat pre, and notice the T1 fat sat pre is just as bright as the post. So it's very easy to overcall enhancement if you're not careful about making sure that your pre-study is exactly the same as post-study. This is very commonly done throughout the U.S. in the spine, where people do a T1 non-fat sat pre and a T2 and a T1 fat sat post, and they grossly overcall enhancement. I think the reason that people are able to get away with that is I don't think enhancement is very important for the spine, but we've already talked about that on prior lectures. But if you're looking about for tumor follow-up where it is important and you really have to know whether you have enhancement or not, it's essential that you have exactly the same sequence before as after. The other thing is this is a CT scanner. This is gadolinium in the vial on your left, and this is iodine in the vial on your right. It just shows you that gadolinium is a contrast agent also for CT. And we've had a couple of situations where people have come in and they've had iodine, they've had pacemakers plus iodine sensitivities, so people haven't wanted to do an iodine injection, and we've done arthrogram injections on CT with full-strength gadolinium, and we've got fairly diagnostic studies. This is just a case where you can see the subacromial subdeltoid bursa filling in someone who has a prosthesis here, and that's showing that there's a recurrent tear or a tear in the rotator cuff. Okay.
Dr. Cruz?
Yes.
Quick question: why do we use contrast, gadolinium contrast, and we do a T1? We usually use it with a T1. Why don't we use a T2?
Well, but because as I talked about in this slide, the primary effect that gadolinium has. Well, what is the primary effect that gadolinium has on the tissues? Why did we pick gadolinium? Why did we pick something that's a paramagnetic structure?
Because it has so many paramagnetic. It has I think 7 electrons.
7 unpaired electrons. But why are we picking? Why did they pick a substance with 7 unpaired electrons, which is paramagnetic, to try to use as a contrast agent? What does it do to the tissues?
Toxic. I mean.
Well, we hope it's not toxic. That wouldn't be good.
Why we pick gadolinium over others? Okay. I'm not sure.
Well, wait a second. We've just been talking about what gadolinium does and
right.
what unpaired electrons do. We just talked about how it can affect the growth of the bulk magnetization vector in the Z direction.
Oh, okay.
So what did we say about that?
Yeah, so it shortens T1 time and basically increases the bulk magnetization vector in the Z direction, so you get a
Okay.
stronger signal.
Okay. So if its primary effect is to shorten the T1 time, then what kind of a pulse sequence would you want to use to be very sensitive at picking up its action?
You would want to use T1,
Okay.
um,
Is
but I
wasn't
thought
that your
on
question?
yeah, but I thought on the next on one of the slides, it also shortens T2 time as well.
It shortens T2 only if you give it in very large doses.
Okay, okay,
And
okay,
uh, and it's not very efficient at shortening T2 because it shortens T1 at lower doses than T2. So by the time it shortens T2, it's already shortened the T1.
I
So
got
we
it.
try to
Okay,
pick a dose that has primarily a T1 effect and use a T1 weighted image to detect it.
okay, okay.
Okay, any other questions? All right.